So magic with magnetic fields. I want to talk about a couple topics that center around two applications. One is football tracking, and the other one is enhanced wireless power transfer. What links them together is the physics. So I'm going to talk a little bit about magnetoquasi-statics. And my student actually came up to me and started using this word, and I actually had to look it up and practice saying it. So the magneto means we're dealing with magnetic fields, and the quasi-static basically means the mathematics and the physics looks just like it does when it's static, but it just changes slowly with time. And that means we can treat all of our problems almost like a static problem, which makes things much simpler. All right, so we're going to just do a little bit of a mathematical background of what do we mean by quasi-static. And so what we've got here are Maxwell's equations for the full wave, and then we have the static. And if you remember, it's the E here, and the E here, and the B there, and the B there. It's the cross-coupling that creates propagating waves. So if we remove the cross-coupling, we stop propagating waves, and we end up just with static fields. This is not particularly useful because we just have an electric field due to charge or a magnetic field due to current. What we want to be able to do is sense these fields. So it's nice if we can get these to change with time, and we can sense. So magnetoquasi-statics says, well, we're basically going to have either the electric or the magnetic field change a little bit with time. And what we can do is we can create an electric field from that time-changing magnetic field. So we're going to use this piece here, and we're going to cross out that piece and that piece. So in electroquasi-statics, we generate a magnetic field from a changing electric field. Here, an electric field from a changing magnetic field. So we basically crank up the frequency just enough so that we actually have some time-varying effects. And that allows us to sense. Because if we didn't have a time-changing field, we couldn't sense anything with an antenna. And if you look at the fields from like a dipole antenna, this is in terms of lambda. The red here is the radiating field. This is what will be propagating out from an antenna. And the green is the non-radiating field. And basically, when you're about 1/100th of a wavelength close to a dipole, all you're seeing is this quasi-static. So everything we're going to talk about with quasi-statics means we're very close to the originating antenna. And typically, our wavelength is going to be around 1 kilometer. And we're going to be within 100 meters of it. So we're certainly within 1/10 and oftentimes within 100. I'm going to move on now and talk about a topic in wireless power. And I know there's people here that have done a lot of wireless power, so some of this will be review, but I kind of want to share two insights, which I think are kind of useful, and then some recent work that we've done for using communication in wireless power. So I was in the elevator in grad school, and Harvard has a very small, I wouldn't even call it an engineering department, it's a science. You either did applied physics, applied math, computer science, or other. Was how I was described as other. And so there was some material science and mechanical engineers in the elevator, and he says, oh, it's so cool, I finally learned why trees don't grow taller. Do you know what one of the fundamental limitations are for how high a tree can grow?
Ability to generate capillary force to draw the water on top of the tree.
The professor wins the prize. So the problem is getting the water to the top. Some trees do it a little bit better, but it's capillary action. It's how can I build a tube that can get water up there? If you know, trees don't have a little pump down at the bottom going, right? They just make thin fibers that suck the water up. And I think this is a great analogy for wireless power, because we think about when we move two things apart in wireless power, that somehow maybe the physics change, but it's really just like a tree. As the tree grows taller and taller, getting water to this height or this height or this height, the physics is the same. It just becomes tougher and tougher and tougher. And we're going to talk about that analogy here with wireless power. So we're going to go back to a coil generating a magnetic field. We've already seen the cartoon, and it's the same as the emitter for the football. And what happens if we introduce a second one? Well, we've already seen with magnetoquasi-statics, a field in here can couple over, and I get a voltage on this side. And so now what happens as I move these two apart? By the way, K is how we're measuring these couplings between these two. As I go farther and farther and farther, nothing changes. Nothing changes. The physics is identical. A short tree, a high tree. Why couldn't the tree grow 10 feet taller? Well, maybe if it's a little better, it's got a little bit of tubes, it can grow 10 feet taller. There's nothing physically changing in a system as we move the coils apart. So then why is it hard? If the physics don't change, why is it hard to do wireless power at a distance. And for those of you that know the answer to this, this will seem trivia. For those that don't, the punchline's here at the end. We can model a transformer or two coils in a standard circuit model. And I won't go through it, but you basically can take all of this transformer and the load, and you can reflect it back as an equivalent impedance, ZA, down here. So here's ZA. See if yeah, I've got an image. Here's the reflected impedance, ZA. It's dependent upon M, where M is just proportional to K, and our load. So what we see as we move farther and farther apart, all that happens is our K gets smaller and smaller and smaller. Just like as the tree goes higher and higher and higher, it's harder to pump that water up to the top of the tree. And so this is what happens. As we move farther and farther, this resistor, this reflected impedance, gets smaller and smaller and smaller. The amount of water we can put to the top of the tree just gets less and less and less as it gets taller and taller and taller. But everything is identically the same. So really what the problem with wireless power is it's not a problem of going farther, it's a problem of having a smaller resistance. And in fact, I did some calculations here where I take this is a 30 centimeter loop. Here's coils 1 diameter apart, 4 diameters apart, 8 diameters apart. And I had a 50 ohm load, and I just reflected it back. And I basically said that 50 ohms turns into a half ohm when I'm 1 coil apart. So I'm about this far apart. If I go 4 times, it's about 4 times the distance, that half an ohm turns into 5.3 milliohms. And if I just double the distance, I go at 8 times, I'm now at 5.3 microohms. So if you think about it, delivering power into a 5.3 microohm resistor is really, 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 really hard. And the reason is well, your wire has more than 5.3 microohms. When it was a half an ohm, no problem. When it's 50 ohms, trivial. 5.3 microohms, it gets really, really hard because the loss of my wire is the same as this. And in addition, oftentimes my systems need to see a much higher resistance in order to efficiently transfer power. So I've got to transform this 5.3 microohms to something else. And so you can see as we go up taller, we just get a smaller resistance. And so the problem is not about distance, it's about a smaller resistance. And I think if you focus on that, you've really got the simple and the easiest understanding of the problem of wireless power at larger distances.
Are you trying to model the loss of the field from the distance between the coils through the resistor?
No, all I'm saying is if I had perfectly ideal coils, superconductors, right? As I move those two coils farther and farther apart, this 50 ohms, when reflected from this side back here, looks like a half an ohm, 5.3 milliohms, and 5.3 microohms. As I move the coils apart, at the receiver side, the impedance I see just gets smaller and smaller and smaller. So if I had ideal coils, it doesn't change it. This is just what the impedance looks like here. Does that make sense? Okay.
What's the ultimate goal? Why are you interested in that resistance? What's the significance of the resistance? If you're trying to compare it to the resistance just of the wire itself?
So I'm trying to get you to focus on the resistance because I think that's the right thing to focus on, because then you can do things like compare it to the resistance of the wire and suddenly say, oh, if I don't have an ideal coil, 5.3 microohms is really small to anything practical. The other thing is if my amplifier that needs to drive the system wants to see 2 ohms and it's 5.3 microohms, I have to impedance transform it. So if you think just circuit-wise about a small resistance, you can start to see kind of naturally the challenges that come about by having a 5 microohm resistor.
I guess that's what I understand. It seems like why couldn't you just impedance transform?
We'll get there. Absolutely, absolutely, absolutely. Okay, so we go here. All right. So there's 3 challenges in wireless power. The first one is you want to minimize radiation resistance. If we go all the way back to the first slide, I said if you're really close to the transmitter, you mainly see the magnetic field. But there was that red curve, right? So there was a little bit of power being transmitted. So even though I talk about my football just having a static magnetic field, there's a little bit of power that actually is going out. And we can represent that power as a radiation resistance, and we just want to make sure that's really small. And usually it is. The other thing is we want the wire resistance to be much smaller than, I call this the resistance of a wireless power. This is this 5 microohms I was talking about. We want our wire resistance to be much smaller because if it's on the same order, we're going to lose half our energy in here and half our energy there. And finally, we need to deliver power from the source. And to do that, we typically want this to be impedance matched with that. Some people argue that they don't need to be impedance matched, but I'm a PA guy, power amplifier. Whatever oscillator I'm having driving this is going to want to see a specific impedance. And that's going to be something that's not 0. It's going to be something that we want to match to this. So we have to impedance transform this. Even if this was 1 micro and this was 1 micro and this was 5 microohms, I still have to impedance match it to that. So that is exactly the third challenge that we have. And so how have people dealt with these 3 challenges? So inductive power transfer, this is a paper from 1977. This is a biomedical application. I don't have it here, but if you look at the citations, it's really interesting. Up until the guys at Whitricity published their paper, this thing had maybe, I don't know, 100 citations. Since then, it's now up to over 1,000. So, and it's 30 years old. So for 30 years, it would lay dormant, and then suddenly people were like, hey, you guys knew all this way back then. And you can see this equation here for efficiency. If you're into wireless power, this is in everybody's paper, k squared QQ. Okay. So inductive power transfer uses standard circuit methods to do the impedance match. Okay, I said the radiation resistance was small, and I'm going to assume our wire resistance is small. So the only thing I have to do to first order is do this impedance match. And so one thing you can do is you can just use a circuit to impedance match. And in this case, I used a standard antenna tuner for AM radio. And the capacitance compensates for the inductance of the coil, and it also transforms the impedance, so my 5 microohms gets transformed to some useful impedance, in this case 50 ohms. And so what I did is I built an inductive power transfer system. Here's my coils. Here's my standard circuit topology. This looks just like that paper from 1977. Because I'm an academic and I'm in the lab, I'm using 50 ohms of my VNA to do measurements. These could be 2 ohms, 20 ohms, whatever you would need. And I'm impedance matching everything. And what I do is I go and measure Gmax. Gmax is the maximum power transfer I could get if I tuned everything perfect and was perfectly impedance matched. This GP here is my S21 squared is actually what I get when I do tune it. And you can see I get pretty close. So I'm actually able to get the theoretical optimal performance out of this inductive system. And this is around 80%. I want to put your attention to this. The T-match here, the loss of my tuner, I de-embedded. Okay? So maybe there's another way I can do this impedance match. And so have people in the literature done impedance matches from very small resistances to big resistances before? And the answer is yes. Is anybody here a ham radio operator? All right, you've probably seen a mini loop antenna before. So this is an antenna that's trying to transmit at a wavelength of a kilometer, but itself is only a meter. And so it uses some tricks to be very efficient. And what it does is it uses a large coil with a resonant capacitor, and then it uses another secondary coil as a transformer to do an impedance match. And remember back at this picture I talked about this radiation resistance, and I said ignore it, it's small, I'm not radiating that much. What people are trying to do in the ham radio world is they're actually trying to maximize this. They're trying to impedance match to that instead of wireless power. And this is where the technique came from. And so here's a paper from 1979 where they introduced this idea of a resonator with a capacitor and a coupled coil. And the whole idea that they wanted to do is they wanted to get their transmitter for ham radio to impedance match to a really, really small radiation resistance so they could use a small antenna, and those radiation resistances are usually around 1 milliohm. So you can already see the problem they were trying to solve is exactly what wireless power. They wanted to get power into a very small resistor. For them, the resistor was the effective radiation. For wireless power, it's getting energy into the load. And we'll go from here. So what I can do is I can take this system and say, you know, instead of using this circuit inductive impedance match, I'm just going to use what guys did in the 70s for ham radio, and I'm going to build this. Okay? So this is exactly out of the paper from 1970. I've taken my coil, I've put a capacitor on it, I have a feed coil, and I built a little transformer. All I'm doing is impedance transforming this 50 ohms to whatever is the reflected impedance. Now, if this is the load, remember it reflects over. I've got 5 microohms here. This system's taking the 5 microohms and impedance matching it to 50 ohms. And once again, this is from the 1979 paper. And for those of you that are familiar with the science paper, you can see that these two are exactly the same circuit. All that the strongly coupled magnetic resonance is just a standard impedance matching technique that ham guys have been using for 40 years. And so what I did is I built this system using exactly the same coils. Everything's the same except I got rid of the T-match and I put in this coil and I measured the, here's the G-max. It should be exactly the same as before. And here's actually what I achieve with the mini loop impedance match. And here is with the T-match. Now remember, I told you I de-embedded the loss of that system, and that's why it's a little bit higher. And so what we can see here is that back in the 70s, we already knew exactly how wireless power worked for inductive power transform. It had to do with just finding an efficient way to do an impedance transformer. And the ham radio guys knew how to do that for a small resistance. It was using these coupled coils. And recently, the entire media frenzy around strongly coupled magnetic resonance is just, I'll say, a marketing way of describing a technique that we've used for quite some time. And so I don't believe the technique is very new. However, I think the paper was important because the science paper reignited an interest in wireless power because people had sort of thought that wireless power was only good for things that were close up. And they sort of got us to reimagine the fact that it could be a meter or 2 meters away. So I think the biggest impact, the science paper from the guys up at MIT, was not to introduce anything new in a technology standpoint, but to reawaken the discussion. And I think there's been, I would say, at least thousands of papers in wireless power since that paper came out. And so here's our paper in Applied Physics Letters, experimental demonstration of the equivalence of inductive and strongly coupled magnetic resonance in wireless power transfer. Mesam at Gavanalu at Georgia Tech did a similar paper, and then there was another paper done also here. So several people have published on this. This isn't my opinion. This is documented across the way. So I wanted to leave you with that thought of strongly coupled magnetic resonance, inductive power transfer are identical. And so why is wireless power suddenly new? Why are we suddenly interested in it? And Mark Allen at Georgia Tech was giving me a ride to the airport once, and he said, it's not that there's anything new in wireless power transfer since Tesla. It's that the power needed has become much less. In Tesla's time, we needed hundreds of watts, and today we need hundreds of microwatts. And I think Professor Reynolds has demonstrated that with some of his very low power radios. That now we can do something with microwatts and tens of watts that we couldn't before. All right, so how can we improve upon this? Well, what if I put in a water tank halfway up the tree? Then I could start my capillary action right from there, right? The difficulty is getting it from the pool up to here, but if I put another reservoir halfway up the tree, we could do it, right? Why not do this with wireless power? Why don't I put a reservoir in between this to see if I can figure out a way to store energy between the two? And in fact, if you were able to put the distance, if the distance between here and a reservoir, if that is half of the total distance, we have 10 times an increase in coupling. It's a nonlinear increase. And so if you look at the increase in efficiency, we actually don't get just twice. We're actually getting usually an order of magnitude increase by having a tank that's able to relay that energy. So what might we use for storage tanks? One thing we could use is a magnetic resonator, which I'll talk about. This could be a simple LC resonator. And we'll talk a little bit about metamaterials. Have people here heard about metamaterials and wireless power? So I want to show you a little bit about how they work, and I have a few movies for that. And so a metamaterial is just an artificial material that has properties that we don't find in nature. And the idea is we can build small pieces of circuitry that on a whole act globally different than other materials. And so you can think about a metamaterial atom as being a simple piece of a larger structure. And in wireless power, we do little teeny resonant coils for metamaterials. And so we build a metamaterial out of an array of these small coils. And so here's a picture of one we've done. It's hard to see with this light, but there's little inductors here with small capacitors on here. And here's a 10 by 10 array of these inductors. And we treat this itself as a slab of material with unique properties. And the most unique property is that the permeability, the relative permeability at some frequencies becomes negative. And a negative permeability enables something very special. It enables waves to propagate inside of here. And of course, I would never be here without a video. So you may have heard about the superlens effect. They talk about a metamaterial having a permeability of -1, and they go through some optics arguments showing it can focus. I actually think about it from a microscopic scale, and I think about waves on the metamaterial. So here is my metamaterial. And what I've done is I put a little coil where I have a source. And what's changing here is the frequency. And as I change the frequency, it also changes the permeability. And so what you can see, is it'll repeat here in a second, is that as I get more and more negative, I start to form waves on the surface. There's actual waves propagating out on this material. And those waves are the storage tank, yes?
So what about permittivity?
What's that?
What about permittivity? Because for superlens, you need both to be negative.
So if we're just dealing with a magnetic source, I'm only focusing on the magnetic field. So the permittivity here is 1. But I can generate the magnetic, all of the metamaterials for wireless power all have a permittivity, a relative permittivity of 1. And if you're talking about light where you have a propagating wave and you have electric and magnetic field, you need both to be -1. And so you can see all I'm doing with this is this material magically has waves that propagate on it. Think about a pool of water that has waves in it or sloshing around. I could store energy in this waves, and it could be a relay for me. Now, what I've done in this picture is I've actually added the loss of a typical metamaterial. And you notice that you can barely see the waves, and the color isn't nearly as dark. Yes?
Oh, sorry, just scratching my head.
Oh, I'm sorry. And what you can see from the previous diagram is when it's lossly, we get all this great wave action, but a lossless system, we get wave action. A loss-E system, the waves are very faint. And this is really the biggest problem with metamaterials, is those waves that propagate are highly lossy. And so we don't get this beautiful effect we would like. And I've put in what the experts at Duke have called the pretty much the most realistic lower limit for current technology. So this is not I made it super lossy. This is I put in best case scenario for today's materials. This is what it looks like. And so what we wanted to do is we wanted to do a comparative experiment. We wanted to compare air, a metamaterial, and then we wanted to put in just a ring with a capacitor. Just an extra resonator, almost literally like that water tank halfway up the tree. And we wanted to see if the waves propagating in a metamaterial were better than just a simple resonator. And I'll just point out here, in all of our work, we're using this little mini loop impedance transformer. To me, I just ignore it because it's just how we impedance match. We could do the same thing with a T-match. And here are the field profiles. So here's an air, here's the source. You can barely see anything at the receiver at the top. Here's really similar to that picture we saw. Here's the source, and we can sort of see the waves starting. We do see an enhancement up here near the receiver. And here is the field from this resonator sitting here in the center. You can see we've got a huge field up here. Now, here we use the loss of a best case metamaterial. Here we just put in the properties for metal. It turns out the loss of this is much lower than the metamaterial. So one could say this is unfair. You've put in a water tank that's just naturally better than this metamaterial. If the metamaterial, if these had the same loss, maybe we'd see the same improvement. And so what we did is the repeater, that's just the loop with the capacitor, has a natural Q of 550. What we did is we artificially reduced it to 150 so that it would match the Q of our metamaterial. So we added loss to that repeater so that it matches, so the same loss of the repeater, same loss of the metamaterial. And we tried 2 different types of metamaterials. And what you see here is the maximum power transfer efficiency for the high Q of 550. Here it is for the 150, and here it is for the metamaterials. So this is with the magnetostatic waves we saw. Here's with a simple repeater. So using the same loss, we have 2.5 times higher efficiency using a simple repeater. And we went and conducted an experiment where we actually took measurements, and we found that our transfer efficiency between our two loops was 20% efficient in air. With a metamaterial, it went to 40%, and then with a simple ring resonator, it went up to 73%. So adding this intermediate material is just like the water tank. And you can add whatever you want. You can add a metamaterial, you can add a simple resonator. But why the metamaterial approach, I don't believe, has been very successful is not because the physics is bad, it's just current metamaterial technology is very lossy. And there are other ways to put an intermediary circuit to be able to enhance the field. Now, this doesn't shape the field like a superlens would. So if you actually want to shape and do an image, this is not going to do that for you. But just looking at field transfer, it has a significantly higher. And if you look at this, this is 3.5 times what it is in air. All right, and so we've published some papers on repeaters. There's also a Proceedings of the IEEE paper on repeaters. This idea of putting water tanks, these are my water tanks. Here's my starting, here's a water tank, here's another water tank, allows you to go further. That's there. All right, I want to finish with one last topic. And it all starts with a cool idea that I read somewhere on a Sunday morning. And so this was the work of Professor Reynolds on QAM backscattering with UHV tags. And the idea was to do a load modulation on the receiver end and receive that on a transmitter. And he showed they were able to get excellent transmission, 94 megabits. I don't know if you've published faster than that yet. But really the cool idea here is to put the complications of the radio on the transmitter end and make a very simple receiver that would just modulate its load. I looked at this was at 900 megahertz, and I said, why can't we do this for wireless power, for RFID? And so we looked at doing basically the same idea. We took our wireless power system, and all we were going to do is just modulate our load impedance, and what we want to do is see a change in that load impedance at the input, and that'll be something that we can measure. And what's interesting is what we wanted was a constellation at the output, or the transmitter side of our systems, of these blue squares. But the load you put on actually had to be in different places because there's a transfer function across the two coils. So the constellation that you put on the one end of the coils is different than the one that you receive, and that's not surprisingly. Here's some values that we had. Here's the actual receiver. So here's our loads, our inductors and capacitors, and a switch. This is what we attach on the receiving side of our wireless power RFID. And what we did is we did it at 3 distances. This is at, I think, 10 centimeters. Let's see if I get this right. I know. This is 29 centimeters, and this has 17 and 45. So we've gone from here to here to here to a half a meter. And we used the standard QAM down-converting receiver for an INQ channel to measure the received signal. And I tried to make these big, but it's hard to see. So at the close distance, here's our 4 points. At our mid distance, here's our 4 points. And at our far distance, here's our 4 points. And we used a thermal color plot and persistence to try to see these points. And the lack of squareness has to do with the non-idealities in our radio. And then we went ahead and transmitted some signals. And I apologize that the red doesn't show through. So here's near, 17 centimeters. Mid is 28, and far is about a half a meter. So this is 51 kilobits. You can see the near is extremely clear. Even the far, we're getting a clean signal. At 200 kilobits, near we can still see it. Mid we can see it. It's starting to get really ugly here at far. And then at 400 kilobits, we can't see it at near. We basically maxed it out. This is 300 kilobits at far, and this is 153. So here was sort of where we still, between these two, is where we found the ultimate limit. And so what we demonstrated was down here. So we went 3 different distances. We did 400 down to 153 kilobits with a fractional bandwidth of 17% down to 6.5. If you compare that to near field communications and RFID systems right now at 13.56 megahertz, they're doing 400 kilobits down, 100 kilobits up. But notice, I don't have it here, we're operating at 2 megahertz, they're at 13. They're operating at a 3% bandwidth or a 1% bandwidth. And we basically showed you can operate at a much higher. And so I expect actually to get up to megabits per second over a wireless power link here in just a little bit of time. All right. One last thing is a pitch to all of you. If you want to learn about radios, I've launched a full online free course, Radio System Design. We have a full set of lectures, experimental labs, and simulation labs. There's 35 modules, 15 minutes to 30 minutes on all topics of radio, from pulse shaping to noise to how you build a diode mixer for your receiver. We have 8 AWR Simulation Labs that walk you through everything from system design to actually doing the E&M for a branch line coupler. All the files are online. We've also got, this may be a help if you want to push your students how to use a spectrum analyzer or VNA, we've got 2 labs for that. And finally in the class, this is something we do for undergraduates. We actually build a QAM radio at the end of an undergraduate class based upon this. So this is all online. You guys can check it out as reference material. And if you want any more information, I put everything up under my publications. You can find all the videos for the football projects online there, and the radio system course is down here. All right, thank you very much.